I'd like to welcome you to this recording on transparency problem article 6/4 number 1. There are actually 2 of them, but we're going to, for now, only look at the first one. Now let's just read the problem statement. A slender bar of mass m and length L is acted upon by a torsion spring at O, which exerts a counterclockwise couple m on the bar as it swings past the vertical position with angular velocity omega. Now let's interrupt there. We can see here's the bar. It's hinged at O. It's hanging sort of in the vertical plane. And there's the torsional spring. So the torsional spring applies a couple m. That is not indicated, but we can think of m as a couple working clockwise on the bar as it swings past this vertical position at an angular velocity omega. The omega is indicated and its direction is indicated. The normal and tangential axis directions are indicated here. That was chosen. It was chosen with respect to the position of the center of mass of the bar. The center of mass of the bar, of course, it's right in the middle since it's a slender bar. You can it's not specifically mentioned, but you can take it then if it's not mentioned that it's a homogeneous bar. So the center of mass is right in the middle of the bar, in the middle of its length at a distance L/2 from the point of rotation. And so as the center of mass will rotate around in a circular trajectory around the center of rotation, which is the fixed axis of rotation O, it will define the normal direction as from the center of mass towards the fixed axis of rotation, and the tangential direction, of course, in the direction at which the center of mass will be moving, the direction of its velocity, tangential to its trajectory. That is the t direction. Let's continue reading the problem statement. Write the expressions for the n and t components of bearing reaction. Probably should be of the bearing reaction at the bar, or on the bar at this instant. In other words, the reactions at point O on the bar at the moment that the bar is in the vertical position. Okay, so I suppose I can make this full screen. The class of motion that we have here is that of pure rotation, fixed axis rotation about the fixed axis through point O. The next step would be to consider kinematics. The kinematics does not tell us too much, except that of course we know that there's the kinematic relationship between the tangential acceleration of the center of mass and the angular acceleration, but we'll get to that in a moment. So the next step is to draw the free body and kinetic diagrams. So on the left here I've got the free body diagram, on the right as usual the kinetic diagram. If I look at the free body diagram, it should indicate all the forces acting on the system. So first of all we'll have the weight of the bar. The bar is of mass m, so its weight is mg. That will be acting at its center of mass, and it's indicated here at its center of mass mg downwards. Then of course I'll have the 2 unknown bearing reactions on the bar. Well, it's actually one bearing reaction, but it's got unknown magnitude and unknown direction, so I can decompose it into 2 components in the tangential and normal directions, as I've done here. And of course that's actually what they've asked us to calculate, is to calculate the magnitude of these 2 components. If we know the 2 magnitudes, we can actually calculate the overall bearing reaction magnitude using Pythagoras, and we can also calculate its direction, because the direction will be the arctangent of O sub n over O sub t in a direction clockwise rotated from the t-axis. That is if we wanted that. Okay, so these are all the forces acting on the body, and then of course there's a moment, the applied couple m that they've told us, and we assume the couple is in the, of course, as positive also in the same direction as omega. So since omega is counterclockwise, the couple is also taken as counterclockwise positive m. So these are all the forces in a general sense acting on our free body diagram. So if you look at the kinetic diagram, of course the center of mass has an unknown acceleration, unknown in both magnitude and direction, but I can decompose that into a normal and tangential component. So the normal component will be r sub g omega, where r sub g of course is the as a vector is the position vector of the center of mass from O, so it will be the vector starting at O ending at G. So its length is L over 2. And so in this, we actually only use the length. So the R sub G in this expression can actually be replaced by L over 2. Of course, in the kinetic diagram, we multiply the acceleration component with a mass. So this vector here is the mass times R sub G omega squared for the normal acceleration component. And then the mass times tangential acceleration component will be then m times r sub g times alpha, where alpha is the angular acceleration in the counterclockwise direction, same direction as omega. Once again, r sub g being L over 2. And then the only other vector that I need to indicate on my kinetic diagram is that of the moment of inertia times the angular acceleration. The moment of inertia I sub g times alpha, the angular acceleration, and that of course is counterclockwise or anticlockwise in the same direction as m and of course as omega. So these are the two diagrams. The next step is to apply the equations, equation 6.1 or then possibly equation 6.4. So okay, let's look at that then. Applying equation 6.4 says the sum of the moments about the axis of rotation, O, must be the same as the moment of inertia about point O times alpha. So if you look at the free body diagram, the weight doesn't have a moment about point O at this specific position. Note that once this bar is swinged a little bit further, once it's no longer in the vertical position, the weight will have a contribution to the moment about point O. Because the weight will always be vertically downwards, but once the bar is swung a little angle further, let's say angle theta, the weight will be working downwards, but there will be a moment arm of L over 2 times the sine of theta. But for this instant, the weight doesn't have a moment, so we can ignore that. And of course, the two bearing reactions goes through O, so they don't have a contribution to the moment. So the only contributor to the moment about point O on the left-hand side of this equation is just the applied couple M. That must be equal to I sub O times alpha, and of course there the alpha is repeated. I sub O is the third times ml squared. Now this, we haven't spent too much time on this in this module yet. This it's not a definition, it's a calculation. The calculation of the moment of inertia of a homogeneous bar. But you will find this in the tables in the back of in the appendix of Merriam and Craig if you cannot remember having derived this in physics also. The moment of inertia of a homogeneous slender bar about its center of mass is 1 over 12 times ml squared. But if we calculate the moment of inertia using the parallel axis theorem about the end of the bar, it's just a third. It's of course larger because a third is larger than a 12th. So the minimum possible moment of inertia is that about the axis through the center of mass. That is at 1 over 12 ml squared, but at the tip then about an axis through the tip is a third ml squared. So this is then I sub O. And then from this equation, I can then solve for alpha. Alpha is the only unknown here because m is considered, the couple is considered to be a known value. It's the parameter in terms of which we're going to solve the problem. So we can solve for alpha as 3m over ml squared. So next we apply the force equation in the tangential direction. So if you look at the forces in the tangential direction, the only force is O sub t, a component that we'd like to calculate. And that we must equate to the mass times acceleration in the tangential direction, which is only this vector here, m r sub g alpha, and of course R sub G is L over 2, so this gives us this equation here. Now, since we've already calculated alpha in the previous step, we can now substitute alpha in here, and if we do, we find that O sub T is just 3m over 2L. And with that, we've answered one of the questions they've asked us. They asked us to calculate the bearing reaction O sub T and O sub N. So the O sub T has been calculated in terms of the applied couple M at that instant. Now, on the next slide, I'm going to do exactly the same, but in the normal direction. So let's just look at that. The sum of the forces in the normal direction on the left-hand side is, of course, the unknown bearing reaction O sub N that we try to calculate, minus the weight mg. With that, we've exhausted the free body diagram. We need to look at the kinetic diagram. On the kinetic diagram, we have the only acceleration vector component, mass times acceleration vector in the n direction is the normal acceleration, and R sub G here is just L over 2, so we have m L over 2 omega squared as I've indicated it here. Remember, omega was assumed to be given in the problem statement. Omega there wasn't a numerical value given, but you can assume that omega is known the way that the problem statement was stated. So from this, then we can solve for O sub N, and if we do, we find that it's mg times a factor of 1 plus L omega squared over 2g. And with this, we've calculated everything that was asked.